In our example from class today, we examined the effect of the A, the K, the D, and the C on the graph of a base function. That function was y equals the cosine of theta. We're going to look at a second method of achieving the same result for this function here that we began with earlier. And in this approach, as opposed to drawing several different graphs leading up to the final graph, what we're going to do is we're going to study a list of coordinates and apply the transformations to those coordinates, and then take that result, the final result, plot those points, and we should have the same graph at the end. And in fact, we'll compare the graph that we produce using this method against the one that we began with in class. So if you read the excerpted piece that I have from our textbook above, we're going to begin with the key points in one cycle and apply any stretches and compressions and reflections to these points. So what I'd like you to take note of, firstly, is, we'll just grab a highlighter, is we're going to take the x values and we will divide by the value of k to apply any horizontal stretches or compressions. Simultaneously, what we'll do is we'll then multiply the value of y by a, or the amplitude of the function. So as a result, what we can write down is an abbreviated form of the transformations that we're performing, and that is this. Each xy, the symbol here, the arrow, means maps onto, and they will map onto this new set of coordinates, which again come as a result of dividing each x value by the value of k and multiplying each y value by the value of a. Last but not least, what we'll do is we'll apply the translations. So we will take that set of coordinates, an intermediate set of coordinates, not the original ones, but the ones that were previously transformed, and then to that we will apply the shift of left or right of d, and then we will also apply the value of c, which was the vertical translation, to complete the mapping. So let's move forward by beginning with listing the y values for the parent function cosine of theta. Notice that we do have x scaled in terms of fractions of pi, so our radian values, and the increments are in terms of pi by 2. So at a value of 0, cosine has a value of 1. So visually, remember the graph begins at 1. At pi by 2, it then descends and it hits a 0. At pi, underneath the x-axis, it goes to its minimum at minus 1. At 3 pi by 2, it comes back to 0. And then at 2 pi, it comes back to the maximum at 1. So what we'll do in the next table is we will then take the values that we just came up with. So 0, 1, pi by 2, 0, pi minus 1, 3 pi by 2, 0, and 2 pi comma 1, and we will transform each of those according to the mapping that we need to do. Now recall that when using this mapping notation, we need to look at the values in our function equation to determine the correct operations that will perform to the x and to the y. So if we look at the k value, okay, the k value is here, it's minus 5. So what we would like to do for k, recall that in xy, the x is going to map onto x over k. We'll come back and fill in the y's in a moment. So what that really means is that's going to be equivalent to saying that each x value will be divided by, revise that here, our k value here, 0.5. Let's get those numbers right. Now we're going to take each x and divide it by 0.5. Well, that just so happens to be equivalent to multiplication by 2. So when you divide a number by a half, you're really doubling it. So 2x. So over here with our mapping notation, we're going to show a multiplication of each x coordinate by 2. So through our table, we're simply going to add in a 2 as a factor of each x. On the other hand, what we need to do is to consider what happens to the y values. So in this case, here's where we apply correctly. This time I should identify the minus 5. That is our a value. And we need to multiply each y value by the value of a. So over here we have ay, so we'll see minus 5y. So let's come back here and complete the mapping notation. So minus 5y. So that implies that each y value will get multiplied by a factor of minus 5. And do recall that we do have the original set of y values as 1, 0, minus 1, 0, and positive 1. So at the end of it all, we can now write down a new set of coordinates that come as a result of these transformations. So our first ordered pair, 2 times 0 yields 0, and minus 5 times 1 is minus 5. If we double up pi by 2, or half of pi, we're going to find ourselves at pi. The corresponding y value will be 0. Next one, 2 pi, and minus 5 times minus 1 is plus 5. So you can see the effect of the negative of the a value, which will result in that reflection through the x-axis. If we double up 3 pi over 2, we'll find ourselves at 3 pi, back to 0, given the periodic nature of this cosine curve. And last but not least, 4 pi and minus 5 times 1, we're back to the minimum of minus 5. So at this point in time, you're welcome to plot these 5 coordinates. And notice that the period is going to have to be 4 pi, much like we had in example 1. And once that's graphing done, you can go ahead and complete this example by using the next table. Notice that here in this table, we do have the coordinates that we just came up with on the previous slide. And our task now will be to complete a mapping. Notice that we do have the mapping from, that is an algebraic representation or symbolic representation of the coordinates from the first transformation. But now we're at the stage where we need to perform the translations. Okay, so this is what we're going to do right now. So let's have a look at the function equation and notice that our d value here, pi over 3. So what we're going to do is to add on pi over 3 to the x values. And the reason why we're adding is you might recall that for a factor of x minus 3, we're actually going to be moving the curve to the right pi by 3 units, which is the reason why we need to add pi by 3. Last but not least, take a look at the vertical translation. This quantity is plus 3, so we're going to add 3 to each y value to move the curve up 3 units. So, with that mapping notation completed, we really do have more or less a formula that we can apply to each set of coordinates in the first column. So let's use that right now. Let's set it up. So firstly, what we'll do is we'll take the existing points and the 2x portion, this piece here, refers to these values. So to those, we simply need to add pi over 3 units. So let's go through the table in all cases, and let's add pi over 3 to these. Okay. Now, nextly, what we'll do is we'll concern ourselves with the vertical translation. So notice that the minus 5y we have already designated here. It has been pre-calculated. So we simply need to add 3 to those. So minus 5 plus 3, 0 plus 3, 5 plus 3. There's the maximum of 8 that we had prior to this. 0 plus 3, and lastly minus 5 plus 3, which gives minus 2, which is the minimum that we had determined earlier. So these expressions are equal to, all the way across, just going to pick out a different color to differentiate between one form and the other. So firstly, we'll have pi by 3 and minus 2. The next set of coordinates we have pi over 3. So do recall that pi is the same as 3/3 of pi. Okay, because we are adding fractions or adding thirds, we have to have a common denominator. So 3 plus the 1 that's here will give us 4 pi over 3, comma 3. Nextly, 2 pi. Okay, so imagine what 2 pi would be. So 2 pi would be 6 pi over 3. So 6 plus another 1 would give us 7 pi over 3, comma 8. And last but not least, the final 2. You can probably see a pattern here in the x values in terms of their scaling. So 3 pi in terms of thirds would be 9. So we'll have 10 pi over 3, comma 3. And last but not least, 4 pi would be 12 pi over 3, or 13 pi over 3, comma minus 2. So lastly, what we would do is simply graph only these 5 points and draw a smooth curve through them. The only difference here is that none of the x values are in terms of decimal values, so it will look a little different than the previous example. So I would suggest that you do make those conversions. So what we'll do is we'll then just verify those particular coordinates. So the graph that we have here is the complete product. So if we go back and pick maybe at least 1 or 2 points, let's take, for instance, the first one. So let's focus on using perhaps this one and maybe one other. We'll check those out. Let's check 10 pi over 3 by 3. So pi by 3 minus 2, let's have a look at it. So pi by 3 is roughly here. It's 1.05. And let's see, the y value on that was minus 2. And yes, it does check out. 10 pi by 3, okay, as a decimal equivalent. So 10 pi is approximately, that would give us 31.4 divided by 3. So we're looking at a number that is just slightly greater than 10. So we're just in this range here. And the corresponding y value for that was 3. So let's check that out. And if we work our way up from here, a little bit more than 10, you're going to see, yeah, you'll see that y value occurring. So either way, the graph that we've created matches perfectly to the one that we had in example 1.